Hi, and welcome to the first lecture unit in the new lecture chapter on nonlinear support vector machines and kernelization. This lecture unit is on feature generation for nonlinear separation, so I'll simply explain here that we can still use linear algorithms, linear classifiers like the SVM that I've introduced up to here to generate nonlinear decision boundaries in our original input space, as long as we are okay with generating extra derived features and projecting our data into a richer, higher dimensional feature space. So, and this is exactly what I want to discuss now here. So, for example, assume your data schematically looks like this. There is no chance of squeezing any separating hyperplane between these blue and green dots here. What we could do instead is we could now project the data, for example, into a richer, for example, 3D feature space, and the higher dimensional our feature space becomes, the more likely it is for us to actually have a chance to really separate the data with a linear hyperplane. Here's maybe a somewhat more realistic example, still of a very toy type of nature. So here I have two concentric circles, a blue circle and a green circle. Again, obviously not linearly separable. So what can we do? So what we now want to do is we want to create a so-called feature map of function phi. You can see this basically as a pre-processing step where you project each original point into a new, potentially higher dimensional feature space, capital Phi. And in this case, I'll simply take this new space here where I copy the x1, I copy the x2, and as a third derived feature, I'll use x1 squared plus x2 squared. And in 3 dimensions, this would now look like this. And now you can see we can easily squeeze a hyperplane between these two classes, and our data becomes separable. And if we project that plane back into our original feature space, which was simply r squared, you can see that this is nonlinear. The decision boundary here is nonlinear. And I guess it's also not so difficult for you to see that actually I wouldn't have needed to project into a higher dimensional space. I mean, basically I could have simply used this derived feature here, which simply measures the distance of each point from the origin, and then by using that feature, by thresholding on that feature, I could construct such a circle here. But anyway, in general, what we'll later on do in practice is usually we don't know that exactly such a feature would work for us. So in general, we'll usually either keep the original features or really project into a higher dimensional space and not a lower dimensional one. So what we just did, using these quadratic effects, for example, let's maybe generalize this. So how about if we now create nonlinear feature maps that contain monomials, so higher order interactions between all our original features up to a certain degree. So all of our derived features would look like this. So they could be the original features, they could be products of the original features, and of course, quadratic effects, cubic effects, and so on. And we can now actually count the number of different monomials we could create. So a monomial up to a monomial of degree 3, for example, would be one of the original features times one of the original features times one of the original features. And of course, repetitions are allowed here. So if you have, for example, x1 and x2, for degree 3, you can create something like x1 squared times x2, or something like x2 cubed. That would also be a third order monomial. And there's a simple formula to compute how many monomials there are for exactly degree d, if you're using p variables, in our case p features in the original space. And there's also another simple, so this here is really elementary combinatorics, because you're basically asking for all potential combinations where you allow repetitions from P objects. Yeah? So you have to select D guys from P objects where repetitions are allowed. And if you want to arrive at this formula here, basically assume, so this here counts monomials of exactly degree D, and these counts all of the monomials up to degree D, including D. So in this case, simply assume there's like the 1 is like an extra feature, so you don't have P features, but P plus 1, and then you arrive at this formula here. Because if you have the 1 in there, you can do something like x1 times x2 times 1. Yeah? And that gives you monomials of lower degree as well. And we are subtracting the 1 here because we don't want to have a constant feature in there, which is all 1s. And let's put such a feature extraction now to use. So I'll use this very, very well-known MNIST dataset now, which contains little images of the digits going from 0 to 9. And these are black and white images of 28 times 28 pixels of these handwritten digits. And now we want to train a multi-class classifier that predicts which digit is visible on such a small pictogram. And the data set is of medium size, so it has 70K observations. It has obviously 10 classes. The 10 classes are all of equal size. So we have 7,000 observations per class. And I'll now use an SVM with such a nonlinear feature map. So I'll simply use a linear SVM with such a feature extraction and projecting now the image into a space of all monomials up to degree D. And I'll simply always use here a regularization constant of C equals 1. And then what you can see is if you increase D from 1 to 2 to 3, so 1 would be our regular SVM, basically without feature extraction, and then we go to degree 2 and we go to degree 3, there's a drop in misclassification error. So apparently using all of these higher order effects and interactions seems helpful to us. So in a certain sense, I would now probably want to continue here, maybe even use a degree of 4 or use a degree of 5. Of course, I should also do hyperparameter tuning. I didn't really do this here, so I was a little bit lazy to keep the computations fast and short. I should also maybe add a couple of extra comments here on the experiment. So again, because of, I don't know, fast computations and being somewhat lazy, I only used 700 observations in training, so that's not a lot. And used all of the rest of the observations for testing. And like I said, I didn't do any tuning. Usually you should not do something like this for the SVM. So using the SVM in default configuration usually does not make sense. We have a detailed lecture unit about model selection for the SVM upcoming here in this chapter. And the multi-class problem, I've only introduced until here SVMs for binary classification problems, the multi-class task, and that's quite common and usual in software we handle with the 1 versus 1 approach here. So anyway, I basically simply want to motivate here that using a higher order monomial feature extraction seems interesting to us, and we potentially want to be able to do this in practice, right? So on the other hand, I also already gave you these two formulas here. Maybe this is most interesting for all of the monomials up to degree D, including D. This is becoming a quite large number, even if P is only of moderate size and even if D is of quite small size. So we plotted this here. So actually to keep the numbers somewhat, not extraordinarily really large, we only used a hypothetical image of 16 times 16 pixels, so even less than this super small image here. And here we plotted now the dimensionality of the extracted feature vectors for the monomials up to degree D equals 1, 2, 3, 4, and 5. And you see you very, very quickly reach orders of 10 to the 10. Yeah? And this becomes computationally basically infeasible even for smallish sizes of D. So are we now at a dead end? Can't we use these types of feature extraction mechanisms for medium dimensionality data sets? The answer is no, and this is exactly what there is a very nice and elegant way out of this dilemma, and this is using kernels, and this is exactly what this complete lecture chapter is about.